session will be given by Fernando Benites from FID, and it will be on the classification of large patent descriptions.
Thank you. So, yeah, this is a good introduction. So, I'm Fernando Benites, but this is I joined work with Dominik, Frefel, Meier, and Perruchoud. We are at the FHNW Institute for Data Science. This is it's a study based on a project that we did for a client, and we thought, okay, patents are nice and we can classify them, but they have also these large descriptions, and how we want to deal with them. So, yeah, outline is I talk about patents first, and then I show you why this is relevant data exploration, how it will impact the results, and then what is there, what we could use for tackling this problem, and then some experiments and the conclusions. Why patents are relevant as use case for large companies? Well, there is also legal disputes, right? You do a patent, you want to secure your IP, but sometimes there is a conflict, and it can be quite expensive. It can impact also research, legal departments, and so on. So you want mostly to avoid that as good as you can. Especially there are several use cases. So an IP prosecution litigation, securing a competitive advantage. You don't want that your competitors have a product that's better, that takes more from the market share. But also within development, you want to identify specific trends or a specific type of technology. You want to keep your people up to date with the state of the art and what's been developed and what will be developed in the next time. Also, the checking out the competitors is a possible use case for patent monitoring. And this is not only the pharma as in the first example, but also food, nutrition, tech in general, automobile, chemical industries. And usually they have some query on a specific database, and this query is quite large with keywords. And the result is that they have thousands of patents to review weekly, and the lawyers that do that, they are fed up with irrelevant patents. So how can we do that? Mitigate thousands, maybe to a couple, hundreds, or even some dozens. Is the patent? What's the basic, specific properties of a patent? So these are legal documents, right? You want to secure something, you want that to use in last resort in the court. So they are quite structured. So they have title, claim, description, abstract, although the description is sometimes the main part where the innovation is described, where the background is described, and sometimes there you don't have a specific structure. You want to have this patent filed in a patent office, and this is geographic limited, so you can here in Europe at the European Patent Office, but also there is in the US, in Japan, Korea, China, and so on. They are legal documents, so normally use long sentences. They also have common words used in a specific manner, and sometimes there are terms, legal terms, or tech terms that have also other meanings in common language. So using a general language model can cause problems. and they are just natural language. So you have lots of NLP typical problems like homonyms, synonyms, and you can express certain invention in very different ways. And this is also done by patent lawyers. They want to express very differently the same thing. What does it look like, this patent? So you have an abstract which is short, 700 characters. You can use that in a normal language model like Word. You have 512 tokens input length. This works well. The description is about here 50,000. So it's 70 times larger than what you could use in a in this language models. We think that these abstracts have the really relevant information to differentiate between the fields. We think also that the description is quite long, and it holds also very detailed information. Still, it's very difficult to know what's relevant or not, even for the state-of-the-art models. And we talked to the client, and he said, well, it's nice that you use the abstracts. We see, we read a lot the abstracts, but normally we want also to take a look at the descriptions and see what's really there. And it can help to classify our patterns better. So I remember I organized 2 years ago a shared task on pattern classification, hierarchical pattern classification. It was a German-eval task, also the SwissText. There was about 400,000 training data samples and 600 classes, and I thought, okay, just to check this data set for this use case, it's a bit long. I will take the 19 most frequent classes, and this leaves me with 140,000 patterns. Then we use 125 patterns for training and 60,000 for tests. And they have roughly the same distribution for the classes. You can see there is one class that it's very frequent. The others are mostly in the same area, more or less. There's also a big difference in the abstracts. Also, the example was really a good example. So the mean length of characters per abstract is about 900, and the descriptions are about 56,000. And they have quite different vocabulary. So about 5 million words. And this is a multi-label problem. Not big, 1.2 label density. It means that we have at least one, and in some cases we have 2 labels per patent. The distribution and the test data is roughly the same. And these classes, they are hierarchical organized. We have usually a letter on the top, and then it can go down, and there are about 700 or more classes. I took only these 19 base classes. I didn't regard the hierarchical classification because I thought just will get much bigger than already it is. So these are the 90 classes. They are quite different sometimes, however overlapping. So we have here transmission of digital information, communication in different also forms, lots of electrical and data processing classes. So for this pattern optical tracking, you have two labels in very different branches. One is diagnosis, surgery, identification, the other computing, calculating, counting. I will use in the training, in the experiments, one multi-label classifier. What is quite simple is the binary relevance. It regards the labels independently. So you train per label a classifier. There's also the label power set, which can use the correlations, but usually tries to find unique labels. This makes a lot of classifiers, and we use mainly also neural networks, which use trained with the cross entropy loss function. So it regards the classes, the error per class, and backpropagates this through the network, updating the weights. So what is there for big documents? There is big BERT, which is sparse, attention, and long transformers, which also update only parts of the attention, because the attention training, so the training with increases quadratically with the sequence length, especially the attention mechanisms makes their big problem. There's also the sliding window approach used here into BERT and Robert, not to confuse with Roberta. And yeah, so the sliding window is basically you take 512 tokens of the normal BERT-based models, and you have like 10 tokens overlap, and just move the window, right? So this is your document. You cut one piece, you cut the next piece, overlapping the first piece, and move the window, and so on. Sorry. We use only 30 windows. This, if you see the distribution, how the length of the document and how many documents have this length, we cut around here. So we take most of the documents, but some will just be cut off. This is sure the problem that we don't know where the relevant part of the patent is, so in some documents we may perform worse. We use TF-IDF with support vector machine on top of that, and we use sliding window with average pooling, LSTM, and ensembling. So how does this sliding window also work using BERT? You take just the tokens, put in BERT, and get a class label embedding. So it's the first token we use as the embedding of the document, of this document part. And it has 1024 dimensions. We use also BERT for patterns, which is a model trained by Google on about 100 million pattern documents. And this is the visualization of basically the architecture. We have the BERT, which is applied on each part of the text. We get then an embedding, and then we use an LSTM to go over the embeddings and create another embedding, which we use a full connected layer to predict our classes. We train on titles and abstracts, and then we use also title, abstracts, and the descriptions using the sliding window embedding, sliding window approach. which is roughly about the 6 to 80,000 characters. Use also the metric micro and macro F1 score, and we check sort of confusion matrix, so how many true positives, false negatives, and false positives there are. So this is just on title and abstract results. We get for the TF-IDF SVM unigram, so just use words here, disconnected words, and we get 74 micro and macro 75. Then with the multigram, so 1 to 3 grams words, we get a little better on the macro stays the same, so we gain probably again and then we lose. And for word for patterns, we gain again a little more. We go to 77 micro and macro 76. So when you use the description, we gain a lot of performance improvement. Using average pooling is the least performant, so it's just the mean of the embeddings and then classifying over that. We get 78. Unigram goes up to 79, almost 80 micro. LSTMs go even a little higher. And then if you use the scores of this model and this model, norm it and just sum it, you can get an even higher score of 82, almost 83. We can show here also the distribution of true positives, false negatives, and false positives. Here is the density. It's not. You need to keep in mind that this distribution of classes are very differently distributed. We see here that when we go from TF-IDF to LSTM, there is some push up, and if you go to the ensemble, even higher. And if you check the class distribution, we see that G06F and G06F is quite good. We have a lot of documents there to learn from. But the neighbor key K at the end is quite bad because also we have not many documents there. It's also very difficult, this K, to predict. Here is an example. The G06K is recognition of data, presentation of data, record carries, handling record carries, and they it should be predicted. The first one and the second one is the label that was predicted by our model, our ensemble model, and it was predicted as pictorial communication television. So it is basically a visual measuring device and autofocusing method. So you have here a camera that checks if the measuring device is focused or not, and transmits that to the computer. So there is some relevance there. You can also make the mistake is obvious, but there is some overlap on the meaning. Especially if you look at the text, there is a lot of calculating. Sorry, this was the wrong text. There was another example. This one, there was a lot of calculating in the abstract. So 3 times calculating, calculated, calculating was in the abstract. So in the abstract of stock, there was something about summarization. We took a look at summarization approach, automatic summarization. So take these 50,000 characters, put in it, and get some sort of automatic summarization, and we gave up. Because we try also this big characters, large, if you just this simple text input, replace me by any text you'd like, and it would come. So I'm now single me. This was very discouraging. I tried with the patterns then, because Big Bird was also trained on this big pattern corpus, and it was a quite long abstract, and it just took the first sentence. So not very abstractive, I would say, so we gave up this approach. Classification of patterns is hard. However, TF-IDF is still a good baseline if you have enough data. LSTMs and pattern bird gives you best single classifiers, and then some can improve further the results. Yeah, and this concludes my talk. Thank you.
Are there any questions? Yeah.
Yeah, thanks for the talk. Really interesting. Also the error analysis on classifications. I was wondering, like, what was the data, patterns?
Just the I took.
I mean, like,
take all the patterns from the European Patent Office,
okay, yeah.
download them, and we pre-select some of them, and
okay.
I further melt down to 90 classes.
Because there, like, how are those labels created? There is like a human.
Sometimes a human. Or I think first there is automatic classification. They are then further examined by an expert that gives further labels, but there's a huge hierarchy to the IPC,
yeah.
And sometimes they are, I have the impression they are sometimes random, because it could be either one.
Yeah, that's actually what I wanted to ask, that like maybe look also into like recall at 3 or 5 or whatever, like the next best prediction, whether like the true label is, and
yeah.
Could be also.
This could be interesting, yeah. So I took also from the RARC sample, and it was interesting to see how the algorithms thought about the other classes. Sometimes it was really bad down, also because they are sometimes focusing on what was used and not what was the invention. It's very difficult for this language models to differentiate between what is really relevant for the invention and what's not.
Thank you, Fernando, for the interesting talk. So I also work a bit with patents. Have you compared with clustering methods and also supervised methods, which one works better? Because for us, sometimes you also mentioned some classes, all classes really look similar. So have you tried to cluster them first and also then do the supervision?
This would be interesting. I think no, I didn't actually do that. But also the problem is that also the classes are very, differently distributed, right? Mm-hmm. You have the samples in this big one, and then sometimes in the others, and this makes just complicated to make classes also in the multi-label problem.
Mm-hmm. And the ultimate goal of the system would be to provide a service for LiPo or EPO as an automated tool, or what's the intention behind
Well, the intention was to find to melt down this results of keywords. Normally, the patent lawyers do keyword search first,
yeah,
and then receive this big one list, and then say, well, we do only the keyword on the abstract. We would like to go down in the description and use there also the keywords, but this makes the list just bigger, and our lawyers don't want to check more than 20, 50 patents per week.
Mm-hmm.
So
maybe it would be interesting to apply keyword extractions on the descriptions, and then try to cluster it based on keywords.
Yeah. Well, also the problem is that these keywords are very specific. Sometimes you want to have synonyms of these keywords, and this makes also the list even bigger. But then clustering may be a way to go ahead.
Any other questions? Yes, I was wondering, so these patterns, I don't know what they look like, but I assume they contain
figures as well, and tables, and maybe some formatting. So did you attempt to use other features like layout and visual features for the figures, for example?
No. Also, well, you can get the PDF and go over the layout, right? Still, you need probably then a multi-model model, and then will also be right big and will take a lot of time. Also, the gain, don't know how much gain we'll get there, but it probably will be what we'll be doing in 3 to 5 years. Yes.
Just for curiosity, you showed your coding results or implementation results. Did you try only abstract or only description?
Yeah, the first one was just abstract and title. The second one was abstract and description. You mean just the description?
Just the
No, I didn't try it.
Because the proof was not that crazy from like shift that we showed. And it would be interesting to see if just title like that really boost.
Yeah. Yeah, I can try it and tell you afterwards. Yes, it's not that difficult, but yes, take some week maybe, but yes.
It's also fine.
Yeah.
Any other questions? Yep.
Do you have any strategies for handling synonyms if someone says device instead of instrument?
I hope that language model do that. Yeah. TF-IDF, you could do that also there, but it takes a lot of memory. The moment sklearn TF-IDF can handle so much data. I have also in other projects much more elaborated models, which are sometimes lose, sometimes wins against BERT, but I couldn't do that because just the memory needs more than 50 gigabytes to process the data.
And one tiny thing on slide 23, when you're like showing all the models, like the micro and the macro score, for TF-IDF,
This one?
yeah, exactly. So
I did just unigram, even not multigram, because yeah, more than 50 gigabytes.
yeah, okay, that's okay. So I'm a little bit confused. Like for the TF-IDF SVM model, why is the F1 macro larger than the other ones? Like, can you like explain a bit for that, or?
So why the macro is so bigger than the micro, right?
Yeah, like in all the other cases, the macro is always lower.
Probably some keywords are better recognized on the small classes.
Mm.
This pushes up, and the big one class is sometimes often what I saw is confused with others, and this diminish basically the micro, right? And it also depends how much. So my threshold was here not 0. I push up a little because they tend to be more precision oriented.
Mm.
And if I lower, maybe it's better micro than macro.
Yeah, because that kind of stood out to me a little bit. Yeah. That's it.
Good. Thank you very much. Here's now a break, half an hour, and then the second keynote.